So in this segment, what we're going to do is talk about two important concepts. The concept of correlation, which is to say two variables that tend to behave in the same or opposite ways in a series of observations or a sample, and interaction, which is significantly different. Interaction involves variables that work together in combination as opposed to individually. And I'll give you some examples that will help us distinguish the two. And one of our surveys is specifically focused on demonstrating this difference between correlation and interaction. So what are we trying to accomplish in this particular lecture? Well, for one thing, we want you to fill out the height and weight survey, and in the case of this video, we're going to take the results of the height and ideal weight survey and analyze them to see if those two values are correlated. Then we will talk briefly about preparing the data for analysis. I'm going to largely skip over the slides here in the video. I'll talk about them briefly, and I might create another video specifically associated with how I moved the data down and massaged it. Then we're going to take a look at correlation, and we'll look at the correlation, the degree to which height and ideal weight are related to each other. We will then do the food and toppings survey, which is a survey that I specifically created in the hope of demonstrating an interaction effect. And once again, using your data, we will prepare and analyze the survey and then discuss the results. And in that particular survey, one of the things we'll see is that we do in fact have a very strong interaction between some of our variables, which means we wouldn't want to make a model that assumes that the variables operate independently of each other. So, because the workshop was very data-driven, what we did was we had everyone fill out a form, and in that form they specified their ideal weight and their height in feet and inches. And part of the reason I had everyone specify their height in that way was to demonstrate, how cleanup needs to be made. So what I did was I created an analysis spreadsheet that had a tab that sort of cleans up the data. And there were three different ways in which I needed to clean up the data before we moved it into the JASP package. One, because correlation analysis requires numeric data, what I needed to do was I needed to change male and female, the gender, to a 0 and 1 value. And so I did that with an if formula, where I basically said, okay, if the value in the raw data was female, we'll set that as a value of 1, otherwise we'll set it as a value of 0. This is the Excel if statement, and the way the Excel if statement works is it does a test. If the test is true, it chooses the value after the comma. If the test is false, it chooses the next value. So the if statement always has three values: the test, the value if the test is true, and the value if the test is false. Now the other thing I had to do was adjust feet and inches to turn them into a single number. Otherwise, I'm going to have a lot more problem with my analysis. So what this formula does here is it basically takes the value in feet, multiplies it by 12, which converts it to inches, and then adds it to the value in inches. So 6'1" becomes, for example, 73 inches. So once we have all those values, we are then ready to begin our analysis using JASP. So once again, I'm going to break away from the slide deck and use JASP. So I will open up JASP. I will then I'll go into my computer. I'll go into the workshop where I've got the adjusted survey form, survey 2. This would be, let's see, the height and weight. cleaned up, cleaned height and weight, and I think okay, so I'll bring that up. So now what we have is the gender coded. 1 is female, 0 is male, the ideal height and the ideal weight ideal weight in pounds and height in inches. All right, so now what I'm going to do is I'm going to go over to regression, which is, and then I will create a correlation matrix. And the first values I will correlate are ideal weight and height in inches. And the correlation matrix here, I'll expand this so we can see it a little better. Maybe I'll drag it over a little bit here. And so what we see is there's a correlation of 0.815, which is a really good correlation for cross-sectional data. And here is the p-value. And what would we expect the p-value to represent? Well, what the p-value represents is the likelihood that the variables would have this correlation just randomly. In other words, we had a set of random variables. And what we're saying is there's less than a 1 in 1,000 chance that if there's no relationship, we'd actually see a correlation this high. So that gives us a pretty good confidence that there is in fact a relationship between height and weight. Now it doesn't have to be a nice straight line. We can add gender in here, and gender will give us a correlation as well because we've set it for 0 and 1. And what we'd expect is if there is a difference between the average male and female heights, we would expect a negative correlation because we would expect having a value of 1 in gender, which remember is female, will tend to produce a slightly lower height and a slightly lower weight. So when we add this in, what we can now do is we can open this up and see if we were correct. So what we see here is a negative correlation between weight and gender, meaning that in general the women were likely to have lower ideal weights than the men, and also a negative correlation in height, meaning that on average within our sample, the women had a lower value for height than the men did. So a correlation matrix only shows either the top half or the bottom half because the correlations are symmetrical. So we'd have exactly the same correlations on the bottom as the top half. So it almost always is displayed as a triangle. Some statistical packages will put other information like the square of the correlation down at the bottom half just to fill out the whole matrix, but most of them try not to confuse us. And what we see here is the p-values are all significant. So we're seeing a significant difference in all 3 correlations. So, what does all this mean? Well, let's talk a little bit about what correlations actually mean to us. So, the first thing is the correlation coefficient ranges from -1 to +1. 0 means the variables are not related at all. There's basically no relationship. It's actually very hard to get 0 correlation if you have random variables. You almost always get a little bit of correlation. A positive correlation means they move in the same direction. A negative correlation means that they move in the opposite direction. So, for example, we might find that whereas, well, we already saw that. We saw in women, if we coded women as 1 and men as 0, that was a negative correlation. If we'd done the opposite coding, 0 for women and 1 for men, we would have seen a positive correlation. So that is positive versus negative values. Interpreting the p-values, the p-values are basically telling us the likelihood that that correlation would have been achieved just randomly. When you have very small numbers of observations, you have to have a pretty high correlation before you've got a p-value less than 0.05. If you have thousands of observations, even small correlations will produce low p-values. Once again, because the more observations you have, the more you can kind of zero in on whether or not the relationship is real or not. The gender coefficient correlation, I think we've already talked about that enough. It basically is a way of It's basically saying that the average for the value of gender of 1 is lower than the average for the value of gender of 0 for ideal height and, or rather, ideal weight and height. Correlation versus causation. Correlations work in both directions. So having a correlation in and of itself is no evidence of causation whatsoever. In addition, when you're dealing with values that vary over time, you will almost always get fairly high correlations of any variables that have a trend. So, in the world of climate change, they've demonstrated a strong correlation between carbon dioxide and temperatures. So I started experimenting around with other variables, and I found an even slightly stronger correlation between the consumer price index and global temperatures. The difference is there's a lot of science that can be used to explain the carbon dioxide temperature relationship, whereas the science is very weak for temperature versus the consumer price index. But the thing is, any variables that change over time are going to tend to have a high correlation if they have a trend. And if the trends are the same, it will be positive. If the trends are different, it will be negative. Part of what we need to do in research is when we see correlations, we have to develop underlying models and further tests to determine whether causation is really present or not. And one of the ways we do that is by designing experiments. Finally, limitations to correlation. Correlation analysis in itself doesn't necessarily tell you that much, but it's a good starting point to get insights. If you start seeing significant correlations between variables, that's often a starting point where you can start thinking about the question of why these variables might be related. So interaction is often confused with correlation, but is actually quite different, though interactions can in fact produce correlations. Interactions are an effect that occurs when your independent variables, that is the variables that you are measuring, affect the variable you're trying to predict in combination much more than they do individually. So let's take the example that I nearly always use, which is the example of recipes. If we ask the question, is garlic a good ingredient? That is basically asking, what is the individual or the main effect of garlic? Well, the real answer to that in a cooking context is it depends. If you're making dishes with lamb, so if garlic is used in combination with lamb, garlic is almost always a beneficial ingredient. When you're talking about making desserts, for the most part, garlic is not likely to be your preferred ingredient. So as a result, what we're always trying to do is separate out main effects, that is the effect the variable always has on your dependent variable, from interaction effects. Now, the way we did this in the workshop was we developed a survey which looked at different food combinations, once again, going back to my notion of recipes. And we had two what we would call, main dishes or sort of substrates. Eggplant parmesan fried, or rather eggplant fried, or vanilla ice cream. So we got two sort of main things that are on the bottom, as it were. And then we had two toppings. We had marinara sauce with cheese, and we had butterscotch sauce. Then what we did is we looked at the combination of our main ingredient with our topping. So we looked at eggplant with marinara and eggplant with butterscotch sauce. We looked at vanilla ice cream with marinara and cheese, and vanilla ice cream with butterscotch sauce. And what we asked you to do was to rate each one of these on both nutrition and taste. And the idea there was we would not be able to see a clear main effect for the toppings, the marinara and the butterscotch sauce, because they interacted with the main dish. So that's the basic thing that we were trying to demonstrate here. So the first thing that we had to do was we had to clean up the data. And since this is a very specialized test, I don't even think I'm going to create a video for it, but I'll give you a big picture. The idea is, for every response, what we wanted to do was we wanted to identify what combination of ingredients it had. Did it have ice cream and butterscotch, ice cream and marinara, eggplant and marinara, eggplant and butterscotch, ice cream alone, or eggplant alone? And so for each response, we created this kind of combination thing, so we could look at the variables independently and in combination. And one of the things that we did here was we were not so worried about doing statistical analysis on this, because we were just going to use it to produce spreadsheet graphs. Now, one thing that we could do was we could actually do a correlation analysis. And so what we will do is we'll open up JASP. We will open up a cleaned interaction data. This is the data after I cleaned it up. Then we will come over and do our correlation matrix. And we'll take a look at taste all the way through the marinara and butterscotch, and we'll come over here, and so we can now look at this correlation here. I guess what I'll do is I'll drag this over just to demonstrate that we do in fact have some significant correlations here. For example, when you look at taste, ice cream was positively correlated with taste. The p-value was just a little bit low. Taste and nutrition were correlated. Whether or not they should have been, that's another issue. Eggplant, they weren't so wild about the taste. Marinara sauce, they weren't that wild about the taste. And butterscotch, they weren't that wild, though this is not significant. If you take a look at ice cream versus nutrition, they didn't think that ice cream was that nutritious. They did think that eggplant was somewhat nutritious. Marinara, not significantly nutritious. Butterscotch sauce by itself, highly negative in terms of nutrition. And so basically there are correlations here, but really correlations don't tell us very much. So we're going to close this. We'll just close this out. And now we'll take a look at some things that might help us interpret this data better. So what I have done here is I have basically looked at the presence of butterscotch, either none or present, and looked at it with ice cream and eggplant. So we have four possible combinations: ice cream with no butterscotch, ice cream with butterscotch, eggplant with no butterscotch, eggplant with butterscotch. And what we see here is that whereas the presence of butterscotch seems to slightly increase the taste of ice cream, because this is the taste version here, it definitely reduces the taste of eggplant. And this is pretty characteristic of interaction graphs. The lines are not parallel, and sometimes they cross each other, as they do here. So in the case of marinara, when you have ice cream without marinara, it's up at this high average. When you have it with marinara, it's very low. On the other hand, eggplant starts at a somewhat lower average for taste, but when you add marinara, the taste increases. So in one case, marinara drops the taste down, and the other, it increases it. And that's the same thing as here with butterscotch. That is typical of an interaction effect. So you really can't know what the effect of butterscotch or marinara is until you know if the main dish is ice cream or eggplant. And this is looking at it in terms of taste. Now, my expectation was when we looked at it in terms of nutrition, we probably would not see as much interaction. And certainly in the case of marinara, the lines are nearly parallel, which is to say that when classifying the nutrition, the presence of marinara produced a slight decline in the perceived nutrition when combined with ice cream, and a slight decline in the perceived nutrition when combined with eggplant. I didn't really expect that because marinara is actually pretty nutritious, so I would have expected it to increase, but this is the challenge you have with data. Now, when you looked at the butterscotch, on the other hand, we saw a decline in nutrition when butterscotch was added in both cases, but the decline was much bigger for eggplant. And this suggests to me that perhaps the respondents were having a trouble distinguishing between the taste and the nutrition. But once again, that's something that would require additional investigation. Certainly, you could argue that butterscotch nearly always reduces nutrition because butterscotch is basically sugar, so it basically has a lot of empty calories. But I'm not sure why it would reduce the nutritional content better why it would have more of a reduction in nutrition for eggplant than for ice cream. In fact, I would argue, since ice cream has a lot of calories and butterscotch might make you eat more of it, if there was any interaction, I'd expect the interaction to be stronger with ice cream. But once again, this is data, and certainly in this bottom case here of marinara sauce, what we see is there isn't such a big interaction effect. Pretty much everyone thinks that adding marinara and cheese reduces the nutrition slightly in both cases. And if these lines were parallel, it would reduce it by the same amount, which would be evidence of no interaction whatsoever. So if we look at the roadmap we created from the second presentation, we've now covered correlation and interaction. The next thing that we'll talk about are linear models, and we'll have another way of looking at height versus ideal weight. Then we will talk a little bit about covariates. These are these variables which we believe are going to have an impact on a relationship that we want to separate out when we're not specifically interested in them for looking at the relationship. And we'll look at how gender might affect the height versus weight relationship. Then we'll talk about the challenge of multiple dependent variables, where you're basically trying to predict or understand more than one variable. And then finally, we'll talk a little bit more about this notion of modeling versus testing.